Good morning. Thanks to libDVD CSS and related developments, we geeks, people who didn't pay the Microsoft tax, could watch commercial content. With the advent of the new high-capacity, high-definition formats, this may no longer be the case because there is new encryption on it. What the whole story on this will be told to us this morning by Peter Eckersley of the Electronic Frontier Foundation, who's come over to Berlin from over the big pond. So let's welcome Peter.
Thank you. How's this mic working here? Can you all hear me clearly? That would be a no. How about here? Is this better? Hang on, I'm going to raise this. How's that? Excellent. So as was just said, I'm going to be talking about AACS today. AACS, as you probably know, is the DRM system that's used for high-definition video discs. It's actually used for two different high-definition video disc formats. HD DVD and Blu-ray both use this DRM system. It should be noted that Blu-ray also uses potentially a second DRM system called BD+, which is beyond the scope of the talk that I'm going to give today. It's a whole other thing to talk about. But HD DVD definitely uses AACS all of the time. Well, it doesn't have to use it, but all of Hollywood's content is using it. And this DRM system is incredibly elaborate compared to most of the historical DRM systems that we've seen. In addition to the basic content encryption, it has at least 4 revocation mechanisms, means by which keys or subsystems can be turned off or disabled if Hollywood finds evidence that hackers have started finding a way around the DRM system. It contains at least 3 watermarking schemes, and counting them exactly is actually kind of tricky. And lastly, it contains multiple separate security models that you need to think about when you're analyzing how this system works. And when you look at all of these different subsystems in combination, it has well over a dozen different kinds of keys, maybe even almost 20 different types of keys in the system. And even counting the number of different kinds of keys is complicated, as we'll see later in the talk. So, how many people in the audience remember a number starting with 09F9? Can I see hands? Certainly some of you. And if you saw that number, you might have remembered there was a big scandal earlier this year when a lot of users started posting copies of this key on the website Dig in particular. And here is just one example. Unfortunately, it's not very clear, but this is an AACS processing key in the form of a quiz. So you can see the different quiz questions. You know, what's the directory assistance number in Moscow, Russia? Well, it's 09. What's the function key on your computer keyboard between F8 and F10? Well, it's F9. My favorite quiz question here is the question down. It's number 7. Non-immigrant visa allowing Australian citizens to live and work in the United States. And that's the visa I have to work at EFF, so it's E3 in here, the 7th double digit in the key. So this is an AACS processing key, and of course when this key was published on the internet, everyone was saying, well, AACS is kind of broken, but in fact it's more complicated than that. And so the objective of the talk that I'm giving today is going to be to explain how the different subsystems of AACS fit together, and what keys they use, for example, the processing key that we just saw, and what role those play. To try and answer what the implications of this standard for DRM will be for free software and the open source software world. And also to reduce what I would almost call a denial of service against researchers or programmers who need to work around high definition video, because if you look at the specifications for AACS, they're enormous. They're like many hundreds of pages of technical documentation. They refer to complicated articles in the computer science literature. So if you want to actually understand how the system works, it's very time consuming. And so this is part of a project to try and explain how AACS works in slightly more practical, understandable terms. And so it's part of our work at EFF internally, and it seems worthwhile to report on the progress of our internal understanding of this DRM to the community. Most of the information in the talk is based on public sources. You can go and find these specification documents or these articles on the web. There are a few private sources as well. In particular, there's a tutorial that's a semi-private source that is written by Jeff Lotspeich, who's the principal author of this system. He actually talks to hackers quite a lot. He's, unlike some DRM authors, he's engaged with his adversaries. The system's complicated. So there's almost certainly a mistake or two in my talk. You know, if anyone spots one or knows the system well, that kind of feedback is really helpful. And we're going to try and get all of our material reviewed, so the PDF that eventually will appear for this talk should be slightly more reliable. So what is this, DRM system, this beast? It's zombie DRM. Unlike most of the DRM systems that we've fought, or the community has sort of had to work around, to make free software DVD players, for example, this AACS is zombie DRM. When you think you've killed it, it comes back, from the dead and comes after you again. And that's perhaps the core and most important subsystem of AACS, this media encryption. It's a broadcast media encryption scheme that features revocation for receivers. So if the AACS licensing authority or AACS LA, the people who run the DRM system, find out that your player is leaking keys or content or something, they can turn off the ability for your device to read future disks. And that's a fairly new and innovative feature for a widely deployed DRM system, particularly in the way that it's implemented. In addition to that basic zombie feature that AACS has, it has a system of mutual authentication and revocation whereby drives and software players each know about the other, authenticate the other, and keep blacklists of drives or software players that they're no longer allowed to talk to if those devices have been revoked. It contains a very sophisticated video watermarking and tracer tracing system for finding out when copies of movies are leaking or being decrypted or whatever, finding out whose keys and whose devices are the sources of those leaks. It also contains 2 audio watermarking schemes, or it's going to. They're not actually present in the deployed systems at the moment. They're called the theatrical and consumer audio watermarking. It has other subsystems as well. Those were the ones that perhaps are most interesting. It has also got a thing called the content revocation system that's mostly used for to combat commercial piracy, probably in countries where there are large CD pressing or DVD pressing plants. It has a managed copy system. It has a facility for downloading extra special features for your films. And there are probably other subsystems as well. It's a very complicated beast. So in addition to all of those things, AACS has a really important property, so I'm going to explain this in 2 slides, and they're probably fairly tricky slides, so paying close attention here is worthwhile. It has 2 robustness models that are different. So some AACS players use what's called the hardware tamper resistance robustness model. And other AACS players use a model called proactive renewal. And so as the slides indicate, these are mostly for hardware and mostly for software, but not exactly 100% hardware and software. The hardware model can also be used in software if you have something like trusted computing platform stuff on your computer. So if someone implements a software player that has tamper resistance inside a PC, they might be able to include their player in the first security model for this DRM system. And likewise, if someone makes a hardware player that has internet connectivity, and so it can be renewed, the vendor can push updates to that device, then they might decide to use the software security model. But these two models basically partition all AACS players into two groups. And the difference between the two groups is, with the first model, every player gets its own set of what are called device keys. You'll see what device keys are later, but every different player has a different set of keys. And if your player's keys get revoked, that's it, your player is kaput. It's never going to work again. And that's different to the second model, where the device keys are shared by a version of a software application. So a particular version of Power DVD or a particular version of WinDVD will have a set of device keys. And the model is, as soon as someone finds evidence that those keys have been cracked or leaked or released, they will be revoked. And then the vendor of that software will push an update to the users that has some new software security, obfuscation, whatever, to try and stop people from getting the keys. And so the two different models change, the second model changes keys quite rapidly. In addition to these two security models, the drives themselves, or the disks themselves, have two ways of reading the data. And these are associated with two different subsets of device keys. In hardware players, there is an extra piece of information that is read off the disk called the key conversion data, and that's used in the decryption process with the hardware keys. And with the software players that are attached to a drive in a PC, that's not used. And so why? Why are they doing this? And the idea is they want to split people into two groups cryptographically. And this is important because the designers of AACS know a lot about computer security, and they know that if they deploy this kind of system, that in the long term, or even in the medium term, there will be a class break against hardware. Someone will make a hardware player that you can change the firmware on, or you can solder a mod chip onto the circuitry, and you can get the keys out of the hardware player. And they designed the system to try and ensure that no keys that are obtained by that kind of process will ever be useful in a PC in combination with a PC drive. So in order to make a software ripping, some pirate ripping software or backup software or some unauthorized software on a PC, you need keys that come from one of these implementations that does not use KCD. And what is KCD, this key conversion data? We know that it's some extra information that's on the disk, but the implementation details are a secret. So there's something that the hardware players, like your living room HD DVD player, do to read that data, and it's not publicly disclosed what physical actions are taken and how complicated they are. So this would be a really interesting subject for research because there's no public information that I've seen, at least, that says anything about what this really is. And so it's quite an interesting security feature that we would like to know more about. Now, as I was saying before, there are a lot of AACS keys. This is a list of some of them, broken down by major subsystems. So this subset difference encryption and revocation system, can you all see that cursor? Is that fairly clear when I use that to highlight parts of the slides? Good. Uses a whole stack of different keys. They're the device keys that I was talking about. And it turns out that device keys can be broken down into all these different subcategories. There are hardware ones, software ones, subsidiary device keys, leaf device keys. There's the processing key, like the 09F9 key that we saw before. There are media keys, volume unique keys, and title keys. And all of these keys are just used in decrypting the subset difference tree and actually decrypting the movie off a disk. In addition to that, you've got these keys that are used for authenticating the drive and the player to each other, the drive and the host to each other. There's a public key for each of them, and then there's a session key that will be used in the future. It's not used yet. And lastly, there's a whole other bunch of keys that you will probably hear about at some point that are used as part of the watermarking system. So there's sequence keys, segment keys, media key variants, volume variant unique keys. There are all these different kinds of keys. I'm actually not going to talk very much about these keys, simply because I don't think I have time to go through all of that stuff in today's talk, but maybe some future talk. So the main encryption system, I'm now going to go into some detail about the algorithm that AACS uses to say, okay, all of you people except you and you and you can play this DVD. And you guys are blocked because we've seen your keys circulated in public. Or we have used our traitor tracing algorithm to figure out that we think probably your keys are being circulated in public, or movies that you've ripped and have leaked somewhere. And so this system allows arbitrary subsets of users to be revoked, and anyone else can play the film. And the data structure that's used to do this is called a subset difference key tree. And this data structure was proposed in the cryptography literature by, in this paper, Naor and Lotspeich. Lotspeich, of course, is, as I said, the guy who's sort of in charge of building this DRM system. And it's a large virtual data structure. It's this huge tree of keys, most of which are not actually physically present on any machines. But there are ways to calculate the keys at times when they're going to be used. So some of the keys are actually around, and most of them are virtual. It allows any arbitrary subset of devices to be revoked. You know, I could revoke half the people in this room and still have a DVD that the other half of the people could play. And the revocation is affected by using a thing called a media key block. It's a header data structure on your disk. So when you get a new disk that's published, you know, this year, that's revoked all of the leaked keys from last year, it will be updated to ensure that only the people who haven't been revoked can play the new disk. So you can always play old disks with old leaked keys, up to some things that I'll talk about later. And every media key block, MKB, uses a different parts of this huge tree of keys. And so the idea behind this tree of keys is that the users are broken into subsets. And every possible subset that the users can be broken into has a processing key. So the 09F9 key is only one of a huge family of possible keys that break the, select out some subset of users. And the way that a processing key is made usable, the way that it's actually a processing key that decrypts a disk rather than just a theoretical processing key, is that on the disk there exists a media key that is encrypted with that processing key. And so as the system goes on, different processing keys will be used, and new disks will have different media keys encrypted with the processing keys that are active on this disk. And you can tell you have been revoked if you are not in any of the subsets that is on a disk. So there's a bunch of processing keys corresponding to a bunch of subsets, and if you're not in one of those subsets, then you can't play the disk. So the subsets, this is a diagram of them. This is a huge tree. I'm, of course, only drawing a very small part of it. It's a binary tree. It has up to 31 layers of depth. And we can think of the users as being these leaf nodes on the bottom line. So if you are a device, you can think of each device as being one of these nodes along here. And the subsets are specified as a subtree somewhere in this huge tree, starting at the node A. And so it's this big cone that falls down from the node A. But there's a second part of the subset, which is that it doesn't contain any of the nodes that are inside another subtree inside that, which is rooted at B. So this is why it's called a subset difference, because you've taken the difference between the subset A and the subset B. So let's talk about how, as I said, every one of these subsets has a processing key. And in order to figure out what that processing key is, we first note that every possible root of a subset has its own key, its own device key. And these keys are secret. They're all held by, except possibly some of the leaves, they're all held by the AACS licensing authority, and they'll never let users see any of those particular keys. But these device keys induce a family of other device keys and processing keys. So you have one of these trees on this slide hanging off every possible node in the first slide. So I unfortunately need to ask you to visualize multi-dimensional data structures while I'm giving the talk. We'll see how that goes. And so inside the subtree that's induced by a particular device key, the processing key for this subset is the device key is generated by the device key at B. And so when I say, okay, we're inducing these keys and somehow one key generates a whole tree of keys, the way that works is these are AES keys, and you do some magic with an AES key and you put it into AES, and then you read out 3 keys worth of data from the AES cipher that you've generated. And the first key that you read out is the left subnode, and that's another device key. Then the second key that you read out is a processing key, and the third thing is the right device key. So you can walk through this data structure. If you've got this key A, you can calculate this key down here by going left, right, 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 and then if you want the processing key from there, you pick out the processing key from that part of the tree. And so the machines that are using this algorithm won't have all of these keys, but if they have a key that's higher up one of these subtrees, they can walk their way down to a particular node. And so if you are in this subset and you want to play a disk or calculate, like do the rest of the encryption that you're allowed to do because you're in this subset, then you will be able to calculate this processing key at B. So that means that a person who's here at C, and C could be anywhere, it could be in any of these nodes along the bottom of this graph, can calculate this processing key. And the question is, that I'm sure you're all wondering, is how is that possible? Oh, and the other important point is that B cannot calculate, because B's inside this group here that's not in the subset. Everyone except B can calculate the key. So how is that possible? And this diagram illustrates how it works. So the user C has the yellow keys on their player. So if you are here, you have these 4 yellow keys. And you'll notice, if you follow the way that you can walk down the graph, the user at C can walk to any of the nodes here, except those that are on the path above them, and they can certainly walk to B here. So any subset that starts at A, in which they're included, they can walk to, with the yellow keys as starting points. So when you look inside a player that is for C, it has these 4 yellow device keys. Now, I don't know, this is probably tricky. I hope as many of you have followed what I just said as possible, but that's the basic way that this algorithm works. And so now we can see, given that mechanism for creating these subset differences, we can see how some of the people in the room are allowed to play the disk, and some of the people in the room are not allowed to play the disk. So let's start at the bottom. Suppose that the people who are yellow smiley faces are going to be allowed to play the disk. And the people who have a red blotch underneath them are not going to be allowed to play the disk. Then there exists an algorithm which I'm not going to go into, but you can look it up in the literature, or you can treat it as a toy exercise. It's not too hard to figure out. You could probably figure it out yourselves. And there's an algorithm for taking this group of revoked users at the bottom and enabled users, and turning that into a set of these subset differences. So the green areas are the areas that are allowed to play the disk, and the red areas are the areas that are revoked. And you can use the processing keys for those subsets on this disk. So this, if you had this system that I've got on this slide on a DVD, it would have 4 processing keys, and each of them would encrypt the same media key. And if you are in any of these green nodes, you can decrypt the media key, and if you're in the red nodes, you can't. So for the computer scientists in the room, I've probably lost everyone else anyway by this point, some notes on the algorithmic efficiency of this system. It allows any R users out of the total group N to be revoked. The header that generates these subsets has a length up to 2R minus 1, with an exception for the 0 case. And on average, if you have random subsets being revoked, the header length is 1.25R. So you have 1.25R processing keys on average for those revoked devices. And then the number of keys that the devices need to have stored on them is given by this formula here. A half log squared n plus a half log n plus 1 keys per device. And that's in the papers on this algorithm, but we don't know if the AACS is actually precisely following the algorithm that's set out in the paper. They could decide to actually set up more subsets than the minimal number that they need. And there are potentially reasons why they might want to do that, especially early on when you have systems like WinDVD and PowerDVD that you know might leak very quickly and you want to specifically revoke them. You might want to have a unique subset for each of those players. And that's not required by the scheme, but they could decide to spend more keys on revocation in order to have better management of the early stages of this DRM system. And we don't know. I mean, so actually anyone who's looked at the headers on these disks could probably tell me the answer to this, but I haven't been examining what's happening with the released disks. There's also a good question about how large N is. And if you read some of the documentation, it says that the infrastructure allows N to be up to 2 to the 31. So you have about 2 billion different players. But the existing players look like they're in a subset of only 2 to the 22 keys if you use this formula, which is only about 4 million players. So that's clearly not enough in the long term. They'll probably move up to more keys later. And so I've talked for a while, and we've seen some keys, and I have a table of these keys that we've talked about so far. And just to see how much complexity is going on here, I can actually show you the table. It doesn't fit in OpenOffice's presentation code because it's too complicated. So I'm going to jump over here. This is the set of keys I've talked about. There's some sub-distinctions that are broken down in the table. So I talked about hardware and software device keys separately. There are leaf keys, which are the keys that are at the bottom of those device key trees that get revoked. There are the processing keys, and then there's a big difference between a theoretical processing key and one that's actually on a disk and you can play a DVD with it. There are the media keys that you get when you have the right processing key. And then there's an intermediate step here with the volume unique key. And finally, you get a title key. And the title key actually lets you play the AES enciphered movie on the disk. And so there's some piracy that's occurring that involves skipping all of the top steps and jumping straight to a title key at the end and just reading a disk off using that. But then you need a big database of these keys, and it needs to be constantly updated, and the database can be traced. And so there are different strategies that people are using to fight this DRM system, and different reinforcement mechanisms that the AACS LA are using to stop people from undoing it. So let's get back to where we were. By the way, that table it will be online, so you can actually examine it at your leisure, because I understand that actually absorbing much information from it during a talk is probably tricky. So I've talked about the main encryption system in AACS. Now we can move on to the other fun stuff that they've put in there to make hackers' lives difficult when they try to work around this, or the free software community's life difficult if they try to write players for it. And there are, as I said before, at least three watermarking systems in place, or potentially in place. Two of them are kind of uninteresting from the point of view of anyone who's been following DRM, because they're a lot like the SDMI audio watermarking system that was famously broken a number of years ago, in that they're a kind of extra signal that's added onto the sound track for a disk. And these aren't being used yet, but they will be used in the future. There's a section in the specification that describes them. Or it doesn't describe how they work, but it says that you will be required to use them in the future. And they're coupled to refuse to play systems. So if you have an AACS player and it's playing back a disk that's maybe not encrypted at all, and it detects one of these watermarks, it will be required to stop playing the disk at that point. And there are two kinds, because one kind, the theatrical watermark, always requires the player to stop. And this watermark will be embedded in the versions of films that are played in cinemas. So if you go and sit in a cinema with a camcorder, or some pirate sits in a cinema with a camcorder and records a film, then the audio soundtrack will contain this watermark. And if they then try to release a DVD that has that watermark present on it, any player that notices the watermark will have to stop playing straight away. And there are no exceptions for the theatrical watermark, because Hollywood says there's no reason why anyone should ever have a copy of the film that was played in a cinema. There's a second watermark, and this is interesting that there's this distinction here, called the consumer watermark. And it's the same. It's a hidden audio signal that you can't hear on top of the soundtrack. But this time around, there's a certain amount of this watermark which is considered to be allowed. And the reason for that, it's quite clever that they did this. The reason for that is if you, say, have a home camcorder and you're filming a birthday party for your kid, and in the background there's a television playing a Hollywood movie, if they hadn't put in this exception, then the camcorder would have picked up the soundtrack from the movie, and then a player would have noticed the watermark and said, oh no, sorry, you can't watch your kid's birthday party because it must be a Hollywood movie, because it had detected the sound in the background. And so they've actually written rules saying, well, okay, 5 minutes of background sound is okay if it's from a movie, but more than 5 minutes it stops. Or some rule like that. We don't actually know how long that time is and how the rule works. But it's kind of interesting that they've, anticipated this problem with this DRM system and then made up their own arbitrary rules about how much background audio is considered legal. And this is going to cause havoc for people who do mashup art, almost certainly, because they might want to grab the soundtrack from one movie and mix it with some other footage or something, and then they'll have to figure out a way to remove these watermarks if they want to do that. These watermarks are perhaps not so concerning because they have a history of breaking, and so it's likely there'll be a filter at some point that someone will write. And so if you are making, you may not still be allowed to do this under many countries' law, but if you're making a mashup and you're taking one soundtrack and some other video, you might be able to go and find some code to remove the watermark, and then you have to consult your lawyer about whether you're allowed to. But there's one other watermark in this AACS system that is much more serious. It's something that we haven't really seen used before. And it's a video watermarking scheme, and you say, okay, video watermarking, well, it's just going to be the same. We'll be able to do a transform, we'll rotate the video a little bit or re-encode it. The watermark will be gone. But actually this watermark is really quite secure. And there's a whole lot of good theory that it's based on. And it's based not upon some kind of subliminal signal inside the video, but upon variant marks that are immune to any kind of transcoding or introduction of noise. And they may, in fact, to illustrate what these marks might be, they may actually be visible. So one idea for such a mark is you have a character on screen talking, and then in the marked version of that moment, there's a twinkle in the character's eye. And in the unmarked version, there's no twinkle. Or maybe another example is that the same scene is shot, but it's shot from a very slightly different camera angle. This would be most applicable if you were doing rendered DreamWorks style films. You just move the camera a tiny little bit. So a human being watching the video will see essentially the same subjective experience, but if you got the two things back and you played them next to each other, you could see the difference between the two. And so no kind of introduction of noise is going to remove those visible differences without massively damaging the actual picture. And so the idea with these marks is you have a bunch of these variant moments inside the film, and then the crypto system ensures that when a particular player reads back the disk, it gets one version of each moment or another. And so, if you just have two variants of each moment, it's a binary system. You get one bit of information for every one of these marks that gets played back. And the standard allows for up to, actually I think that should be 60. The standard allows for up to 60 binary marks, or 6,144 variants of a movie per disc. And the question is, what do they do with these marks? They embed this information somewhere. What do they do with it? And they do traitor tracing. They run these algorithms that are designed to take some circulated films and look at the marks inside them and say, oh, this film that's on this file sharing network came from your player over there. We're going to disable that player tomorrow. And the literature on this, there's actually quite a sophisticated literature on how you do this. And it's kind of trivial if people just play movies, play a bunch of them back, and then release them onto a file sharing network. They're obviously identified by this number, this sequence of marks inside their videos. But the literature anticipates that people might be clever and might get together with their friends and say, well, there are 3 of us and we all have a DVD ripping program. And so we're going to get our 3 copies of the DVD and we're going to mix the watermarks together, and then Hollywood will never know who we are because we'll have a scrambled signal. But the literature actually anticipates these attacks, and they construct codes that are secure against arbitrarily sized groups of users. So you might say, well, we're going to make it secure against 3 people. You know, C, my parameter here is 3. Or you might say, well, let's make it secure against 10 people, so that even if 10 hackers are all combining their watermarks, we'll still be able to figure out at least one member of their group after some period of time. And so the particular algorithm that they're using to do this is secret. We know some of the possibilities that they might be using because there are these papers that have been published that propose different ways of doing it, but we don't know which algorithm from that literature they have chosen, or whether they've made up their own new algorithm. And you have very broad latitude to construct these algorithms because they involve arbitrary choices of error correcting codes. So for people who are computer scientists and are familiar with error correcting codes, essentially these schemes are kinds of error correcting codes constructed over the bits. Now, the numbers in the literature suggest that probably large choices of C, say 10 or anything significantly over that, are going to be prohibitively costly. You need way too many different variations in films in order to construct those. But I just put a caveat before taking any numbers that you should go and look at this literature yourself, because I haven't read all of it. I've only read a couple of papers, and so my estimates of what's going on there are potentially flawed. And 1,024, or 6 times 1,024, is not that many variants compared to the numbers that you need to construct the really fancy codes in the literature. But also note that these attacks are not based on just one disk. The AACS can aggregate this information over multiple disks, and so the code that they have gets longer and longer as more disks get leaked onto file sharing networks. But there is one kind of flaw in the way I think that this is correct. I think there's one important difference between the way that the AACS has implemented this kind of traitor tracing and the way that the literature specifies it. And that is because of the encryption system that means that you can only play one variant off your disk and not other variants with different watermarks. People could probably tell where all the marks are in the film, and they can tell when they know all of the possible variations in all of the different marks if they have a large library of pirated device keys or sequence keys. So the attackers against this DRM system can actually tell when they've found all of the variations and they're picking a random choice between the 2 variants, like the twinkle or the no twinkle, or they're making some combination of the 2, like half a twinkle, so the AACS can't read that particular bit of information from the video. And so because attackers can see when they've completely removed all of the marks from each copy of the video, and because these Cs are small, they might be able to, if they have enough devices, actually frame innocent users. And that would probably prevent, if it became serious enough, it would probably prevent the AACS from using these traitor tracing schemes, because if they use the traitor tracing scheme to say, aha, you've been leaking videos onto eDonkey, but they're wrong, because actually it's a large group of hackers who are forging the watermarks, then that would probably defeat this part of AACS. And I guess it'll be interesting to see what actually happens in the long term with these contests. So I didn't talk about how they implement the crypto to do the watermarking, but there are these sequence keys that every device has, and there's a big table of sequence keys that people read through to figure out which version of the disk they have or they're allowed to play. And there's another complicated whole table of keys and how they relate together that is missing from my talk if you want to explain all of the implementation details for this. But it's all documented, and we may end up putting up a paper about it too. So I've talked now about the most interesting features of this zombie DRM system. And the next obvious question is, well, so who fights these zombies? And the most dangerous adversary that the zombies seem to have at the moment are located in the Caribbean. They're a company called Sliceoft. They're based in Antigua, obviously for legal reasons. They also have the same people run casinos in the Caribbean. Like they're pretty shady. They sell proprietary Windows binary blobs that break the AACS DRM system. And those binaries are regularly updated. So the way that they defeat the new media key blocks is every time AACS releases a new batch of DVDs that revoke the old keys that Sliceoft were using, just the next, shortly afterwards, there's a new blob that has a new set of device keys or a new set of processing keys or whichever key they've chosen, whichever step they've chosen to break the system at, they've just updated it with a new leaked key. And these guys are obviously, they've got some smart people in a lab and they're paying them good salaries to keep breaking these keys. And they have those updates. Now, the thing that really helps Sliceoft is that the contracts that the AACS have with the disk manufacturers specify a turnaround time of 3 months for key revocation. So it really helps Sliceoft that they always have at least 3 months of good use from each new key that they break. If that was not the case, if the turnaround time for revocation was 2 days or 3 days or something, it might be that Sliceoft would no longer be able to always play the latest disks. But what you would probably see then would be a process whereby if you waited a few months, they could time their releases, and then every time they released a new set of keys, they would liberate the content that had been published in the last few months. So that contract clause certainly helps the pirates here, but it's not absolutely necessary. So, if you're a pirate who wants to share stuff on one of these file sharing networks, obviously this Caribbean stuff is working, and the AACS is not effectively preventing piracy. But where AACS really sucks, where they're winning in their objectives, is in terms of playback on free and open source software platforms. The reasons for this are kind of interesting. It's not the revocation system so much as the fact that host authentication can be revoked. I didn't actually talk about how host revocation works, but as I said, the host and the drive and the software on the PC authenticate each other with public keys. But every disk also contains a list of public keys that are now revoked. So every time they publish a new media key block and a new set of disks, they also revoke the host and drive public keys for any devices that they've seen to have been broken. And the implementation requirements for AACS say, if you make a drive, every time you see a list of revoked software players, you have to remember that list of revoked software players. And every time, and vice versa, if you're a host and you see a list of revoked drives, you have to remember it and then refuse to talk to the other side if they have that public key that's been revoked. And so if you want to write a player on GNU Linux or some other open system, the first thing you're going to need to do is talk to the drive. And it's going to try and do a handshake with you. And what public key are you going to use for that handshake? Well, you're going to have, because the AACS refuses to authorize free software implementations of their standard, you're going to have to find a key somewhere to do the handshake. And if you do that handshake with a host public key that's been revoked, then obviously it's not going to work. So you might briefly have a GNU Linux player, but as soon as you get a new DVD from the video store and you put it into your machine, it's going to revoke your host public key and suddenly your player is going to stop working. And the only ways that are really going to be feasible as a workaround for this is either to have some hacker breaking a new host public key every week in the same way that the Sliceoft people are, but breaking it and actually giving it to the free software community. And that's a lot of work potentially, because these obfuscation systems will be complicated and they'll take time for people to break. And so there might not be this supply of keys for people who want to just watch DVDs on Linux. There's a supply of keys if you're a commercial pirate making money, but the free software community is kind of squeezed in the middle. The other thing that people might do is they might find ways to hack or mod chip the drives so that they no longer do the handshake properly and no longer demand a host key. And that might work, but then you'll be in a situation where if you want to watch a high definition movie on Linux, you'll need to get mod chipped hardware in order to be able to do that, which is pretty bad. It's certainly not the way that we would like to see this space have been designed. There's also the need to have a supply of device keys. The device keys in a Linux player will get revoked, but the difference between those and the host authentication is, of course, the device keys that are circulated will work for all of the old movies. So with Linux players, you'll have this device key that's old, but it'll play all the films that are less than 6 months old, and then someone will come out with a new device key. And so over time, all of this stuff will become playable on Linux in terms of device keys, but not necessarily in terms of authentication. And so what does this mean? Like, what is Hollywood doing to Linux users here? And unfortunately, the straight out answer is that they're driving people to piracy. If HD DVDs don't work on your system, well, you're going to find someone who's leaking the content of those movies in DRM-free formats onto file sharing networks, and you're going to go and download that stuff instead. Or you're going to go and find the guy down in your local shopping mall who will mod chip a player for you or whatever. So Hollywood is really driving people who might just want to buy DVDs and watch them on their computers to actually engage in this whole world of piracy. So here's a little bit of speculation. Here are some like, I'm not dead sure about any of these things, but here, like, we talk about whether AACS has been broken, and the question is whether there are, like, is there kind of a point where you say, actually, it completely failed, and now it's kind of broken forever. And if there's a way to, say, extract key conversion data, then that might lead to people finding a class of hardware players that are easy to get the keys out of. And then if there's that supply of keys and the key conversion data from somewhere else, then you could make software that just picked a different key out of that long supply of hardware keys and use the key conversion data that you normally can't read out of your drive. And then you could probably get a really broken system. If someone found a way to modify a non-KCD player, these are theoretical. I'm not sure that any such players exist, but the specifications kind of allow them. So you have a hardware player that doesn't use the KCD, and then it gets mod chipped. Then that entire class of hardware would provide the keys that would be necessary to make more and more software players. So if someone makes these non-KCD hardware players, and the reasons that people don't make them is because they're more expensive. You have to do more stuff if you make such a player. So the idea is they've designed this to be economically uninteresting for device manufacturers. But if some device manufacturer builds these things and then they get mod chipped or hacked, then the system might actually break. And lastly, if some of the important keys, the ones that no device actually contains, someone found a way to cryptanalyze out the root device keys or something from this system, and maybe that would be possible. Maybe there's some attack that is based on using a lot of crib information or something. It seems unlikely, but if that kind of thing happened, then the system would actually break hard. I guess there are also rumors of side channel attacks against AACS keys. I don't think they're necessary. There was a talk earlier at this conference that I didn't get to go to. I don't know whether that's likely that those kinds of side channel attacks would get you more than just the keys out of a single device. But I'd love to hear about more details on that stuff if anyone's researching it. And so, lastly, I'm just going to briefly mention that the legal structure of AACS, like most modern DRM systems, especially Hollywood's DRM, is based on the idea of hook IP. So if you are going to implement a legal player for this stuff, you have to get either access to some patent license from the AACS people or some trade secret information like the keys. And in order to get access to that information, they will make you sign this huge evil contract that basically creates all these rules saying you have to go to great lengths to make your DRM difficult to break, and they'll charge you money if you fail to do that successfully or whatever. And So there are all these restrictions associated with authorized players resulting from that legal structure. And then, of course, aside from that, if you are outside of the contract, there are still anti-circumvention laws that create huge numbers of legal risks associated with trying to get around these encryption systems. We've published at EFF some legal information about those laws and how they relate to AACS and to people doing research on it. You can find it by Googling 09F9 illegal primer. But unfortunately, that information is specific to the United States and the DMCA because all of our lawyers pretty much work in the United States. And so it turns out that actually the United States is a really unfriendly place to be doing research on this stuff. The law in the United States is really hostile. Other WIPO, almost every country is kind of theoretically required under international treaties to have a DMCA-like law, but the details may vary a lot from country to country, or your country may not have implemented that yet, or whatever. So there may be some jurisdictions where it's more possible to do legal research on this stuff, and provided you don't actually go out and start engaging in widespread piracy, it may be possible to actually do the research on the crypto system. But you should speak if you want to work on this stuff, you should speak to a lawyer in your country. And of course, working for EFF, I definitely can't look at the actual. I can't actually do any research on the details of this system because in the United States, it's certainly pretty risky. And the conclusions? So as I said, AACS is not in any way going to stop large-scale piracy. The slice-off people, the people who have a commercial incentive to figure out ways to break this, people who are going to use slice-off and get big pirate networks together and then break the watermarks and leak all of the stuff onto file-sharing networks. I think Hollywood's going to lose against those people. But at the same time, the real reason that Hollywood keeps using fancy DRM and spending all this money is because it gives them control over legal players and legal platforms for playing back their content. So they can say, we want these features in DVD drives, we don't want those features, we don't want Linux players because Linux players are too easy for people to make copies with, or because we just don't like Linux or whatever. And so the reason that Hollywood keeps doing this is it's because it gives them the kind of power that Apple had over the music industry. If you control the DRM, you call it tune. And so that's really why Hollywood keeps using this, we believe. But unfortunately, it's also a major waste of a lot of really smart people's time. As you can see from looking at this stuff, there are really smart cryptographers who've been designing a really well thought out system. They've made huge numbers of improvements over the kind of DRM that we've seen before. It still doesn't quite work, but and really it seems that those people could be doing something more useful than building DRM systems. And lastly, just about EFF, if you don't know, we're a public interest technology policy organization. We're mostly based in San Francisco, but we have a small office in Brussels and some other people scattered around the place too. We're member funded, so we exist because people join and send us money. And so if you like the work that we do, please come and join, and we'll send you a t-shirt. And you can find us at eff.org. So I think it's time for questions.
Hello. I want to say a few things about AACS. So you talk about you can revoke users. I think that is not correct for now. You need some special keys on the disk, like the PMSN, to revoke specific users. For now, you only can revoke drives, software, and not the specific user.
You're right in the sense that in order to revoke a specific user, really what you revoke is a set of device keys or a leaf in that device key tree. And so whether that key corresponds to an individual depends on whether you are talking about a hardware player or a software player. In the case of a software player, it's certainly true it's not an individual user that gets revoked. But in the case of hardware players, it is actually your hardware that gets revoked. And so, yeah, the answer depends on whether you're talking about hardware or software.
Then you talk a lot about the watermarking. I think that is not practical. No studio invested time to spend a lot of money and time for the watermarking. That's not practical.
Right, so it's certainly true that watermarks, I don't know that the watermarks have actually been seen on the discs yet, but in a sense that's understandable, because if you look at the way that this revocation system works, the watermarks are there to, when you start getting lots of different keys popping up all over the place, they're there to try and help figure out which keys you should revoke. And early on it's easy, you just revoke the Power Now DVD key and the keys for the existing software player versions that are out there. But when you start getting hardware keys cracked, you need more infrastructure to figure out which keys to revoke. And so the prediction from the AACS people was, well, yes, we're expecting to see the studio start doing this in the future. Now, it's true it does require some investment by the studios to put these watermarks there. They need to create 1,000 or 6,000 different variants. They need to create 10 or 60 different places on each, in each movie where the image is different. But honestly, you know, people with a copy of Photoshop or whatever can create those variant marks pretty quickly. And Hollywood spends a huge amount of money on making these films and promoting them. So I actually think we will see these watermarks appearing at some point. You know, yes, it wasn't there in the initial launch of the system, but the cost of doing that is actually pretty small to them, I think. So I mean, I can't guarantee it, but my prediction is they will use this watermarking system.
Hello. Sorry. This guy here wants to cut me up, but I think the AACS contract, you said you get the keys from the AACS LA. That's not true. If you sign a contract, you don't get the keys. Only the AACS holds the keys.
It depends on which keys you're talking about. Obviously, there are plenty of keys that only the AACS gets.
There's no contract. You can get the keys, I think.
Well, the keys I'm talking about are these ones.
If you are the replicator, you don't get the keys. If you are the studio, you don't get the keys.
No, it's the player manufacturers who get the keys, and the keys that they get are these yellow keys.
The only player manufacturer is Toshiba himself. Toshiba is the AACS LA.
Yeah, that's a fair point. I mean, it may be that that's a very closely held contract. But Power Now, WinDVD and Power DVD, those people are also player manufacturers with contracts, and they get these yellow keys in this diagram.
I talked a lot with people from the studios, Hollywood studios, and the most of them don't like AACS, but they need to use it. You need AACS when you want to implement online stuff on your disk, or some features like the persistent storage usage. But the most of the studios don't want to use AACS. It costs a lot of money and time.
So, I mean, that's a strange situation if they actually, I mean, they created this system, it's their, I mean, not exactly them, like there are people, cryptographers in the middle, but it's the studios who are mandating the use of this stuff. They could, in the same way that the music industry has switched to MP3 recently, almost all of it, they could just turn, like, they can't do this with Blu-ray, I believe, but with HD DVD, they can just not use AACS if they want to. And we'd certainly encourage them to stop using it. I mean, it's kind of terrible that all of this stuff is being deployed everywhere.
Okay, you just said Blu-ray. On Blu-ray disc, there's another level of protection which is called BD+. How does this interact with the AACS system?
So unfortunately, I haven't. I'll talk about BD+ for a moment. I haven't had the time to do nearly as much research on BD+ as I have on AACS, so I didn't put that stuff in my talk, one, because I didn't have time, but two, because I don't feel like I'm in a position to comment on it yet. It's harder to figure out how BD+ works because where AACS is a fairly open organization, they publish their specifications and discuss their security model, and all of that's out in the open. And Jeff Lutzbeach is clearly, you know, he's a hacker, he talks to hackers, as his peers, etc. The BD Plus people, if you want to even see a copy of their specifications, you have to pay $2,000 and sign a really evil contract that, there's no way we could sign that contract. But there is one source of information present on BD Plus, which I just haven't had time to properly examine yet, which is the pending patent application on BD Plus. And so you can find that if you go, it's not actually a patent yet, but if you go, there's a database on the United States patent website that lets you see patent applications that are pending. And if you go there and you search for the assignee field, so the company that's applying for the patent is Cryptography Research, which is the company that designed BD Plus. You'll be able to get a copy of the specification, well, not a hint about the specification. And the basic idea of BD Plus is that instead of actually doing all of the playback, the player contains a virtual machine. And then it reads off the disk some code that's signed to run inside the virtual machine. And so the actual code can change from disk to disk, and it can do all sorts of monitoring on its environment to try and work out that it's in an authorized environment. And the idea was to move the incentive, instead of having a player implementer who doesn't really care ultimately if their player is cracked. In fact, they kind of like it if their player is a little insecure, because then people will buy it. The contents of this virtual machine are written by the industry themselves, and they have very strong economic incentives to make it as secure as they can make it. So that's the design philosophy. The other thing that I should note about this is that the presence of BD Plus is an optional feature in Blu-ray discs, and I think it's in addition to AACS. I think that the discs have both. Is a very good reason for people, if you're going to buy one of these standards, I'm not sure that I really like either of them, but if you're going to buy one, it should definitely be HD DVD. And so the community who cares about reducing the amount of DRM we have in this world, you guys obviously have a lot of sway with your friends. If your friends are asking you, should I buy a Blu-ray player or an HD DVD player, the answer is very clear. You want HD DVD out of those two.
So time is running out. Let's thank Peter again for his wonderful talk. Goodbye.